Hey, what's up everyone? Today we're going to be going over the Leetcode or Fang interview level hard problem. Find the median of two sorted arrays, and the solution is going to be in Java. So the general idea is this. To find the median, we need to figure out the middle element of the merged array. That is if the array is odd length, or the two middle elements of the merged array. That is if the array is even length, right? Because we just take the average of those. However, we can actually figure out what those elements are without merging the array. So the solution is this, right? Using a modified binary search, you can find the median of two sorted arrays in logarithmic time, so that it's big O of the log of minimum of m and n, where m and n are the respective lengths of the first and second sorted arrays. We're calling those array 1 and array 2 respectively. So let's visualize this problem. So we can partition the merged array into a left and right half. Let's call it LH and RH respectively. So we can define LH as length depending on whether n is even or odd, right? So if n is even, the length is going to be the quantity m plus n divided by 2, right? Obviously. Now, if n is odd, then the length of LH is going to be the quantity of m plus n plus 1 divided by 2, right? Because LH's length has to be an integer. Now, if we can discover this partition, we have essentially solved the problem, because the median is either going to be the last element of LH, if array length is odd, or average of last element of LH and first element of RH, if the array length is even. Now remember, in order to solve this problem in logarithmic time complexity, we need to discover the LH without actually merging the arrays. So therefore, we're going to need to take a portion of numbers from array 1 and array 2 to construct the LH. So given the set of numbers array 1 at index 0, array 1 at index 1, all the way up to array 1 at index I as the set of numbers we use from array 1, and then similarly array 2 at index 0, array 2 at index 1, all the way up to array 2 at index j as the set of numbers we use from array 2, we can define the set of numbers in the left half, which is simply going to be the quantity listed here, right? So in this diagram, you can see this principle illustrated, right? The contribution of array 1 and array 2 to the left half. All right, so the intricacy lies in determining how many numbers we use from array 1 and how many numbers we use from array 2, right? So in other words, what indexes I and j should be. However, we can conclude a few properties about I and j, right? So we know that each number in LH needs to be less than or equal to each number in RH, right? So in other words, LH at index k is going to be less than or equal to the minimum value of RH. K is going to be an arbitrary index in LH. Now, since the RH is constructed with the remaining elements from array 1 and array 2 that weren't used in LH, and because array 1 and array 2 are sorted arrays, the minimum of RH is going to be the minimum of the value array 1 at index I plus 1 and array 2 at index j plus 1, right? Now, since the minimum element of RH is going to be the minimum of array 1 at index I plus 1 and array 2 at index j plus 1, either the minimum element of RH is going to be array 1 at index I plus 1 or array 2 at index j plus 1, right? So, however, we're already given that array 1 and array 2 are sorted arrays, so we know the following, which is that array 1 at index I is going to be less than or equal to array 1 at index I plus 1 for any index I, right? Array 2 at index j is going to be less than or equal to array 2 at index j plus 1 for any arbitrary index j, right? Therefore, if we just satisfy the following two constraints, right? Array 1 at index I is less than or equal to array 2 at index j plus 1, because we already know that array 1 at index I is less than or equal to array 1 at index I plus 1, right? And vice versa, array 2 at index j is going to be less than or equal to array 1 at index I plus 1, because again, array 2 at index j is already going to be less than or equal to array 2 at index j plus 1, right? Then this set of numbers, right, array 1 at index 0, array 1 at index 1, all the way up to array at index I, right? Array 2 at index 0, array 2 at index 1, all the way up to array 2 at index j, right? All of these numbers are going to be less than or equal to the minimum of array 1 at index I plus 1 and array 2 at index j plus 1, or the minimum element of RH, right? So in other words, index I is the last index of the LH of the merged sorted array, right? So now let's talk about edge cases, right? And again, the constraints that I talked about are right here just for reference, right? So I equals to 0 means that we didn't use any elements from array 1, which means we don't even need to satisfy constraint 1, right? And similarly, j equals to 0 means that we didn't use any elements from array 2, which means we don't need to satisfy constraint 2, right? So the question now becomes, how do we satisfy these two constraints for indexes I and j, right? Which is, again, listed here for reference. So first off, notice that we only need to figure out what index I is, since we can compute index j using the formula j equals the length of LH minus 1, right? Very trivial, okay? So there is this edge case, right? Now, note that the above formula only applies when m is less than or equal to n, since if m is greater than n, there is the possibility that the partition index j is out of range, right? So thus in our algorithm, if m is greater than n, we're just going to need to flop array 1 and array 2. That's a small change that we need to do, but a critical change. Now, we can discover I through a modified binary search, right? Just like in the regular version of a binary search, our left and right pointers point to the start and the last index of the array 1, okay? So while our search range is still valid, which means that start less than or equal to n, of course, we compute and use the current midpoint at our variable name mid at our current partition index I, and we check to see if I satisfies our two constraints. Okay, so this is the breakdown. We have two cases. So case 1, right? If I satisfies our two constraints, then we have found the partition, which means we found the correct value for index I, and we can derive the median based on whether the input array's length n is even or odd, right? So case 1, if n is even, then median is going to be equal to the quantity of the maximum element of LH plus the minimum element of RH divided by 2. And if you just do a simple substitution, right, then you get the expression listed below, right? Now, if n is odd, the median is going to simply be the maximum element of LH, which is going to be the maximum of array 1 at index I and array 2 at index j, right? Now, if not, then, so if I does not satisfy our two constraints, then we need to modify our search range accordingly, right? So case 1 is if array 1 at index I is greater than array 2 at index j plus 1, we need to reduce I, right? So our search for I needs to shift to the left, which means our n pointer is going to now be updated to mid minus 1, right? Now, if array 2 at index j is greater than array 1 at index I plus 1, that means we can increase I, right? So our search for I needs to shift to the right, which means start equals to mid plus 1, right? All right, now let's do the complexity analysis, right? So with regards to time complexity, array 1's length is m, but if m is greater than n, which is array 2's length, we replace array 1 with array 2, so which means that array 1's length becomes n, right? We just swap the two arrays. So in other words, array 1's length is minimum of m and n, right? Now, because we conduct a binary search to find the correct partition at array 1, our time complexity is big O of the log of minimum of m and n, right? Now, with regards to space complexity, we only keep track of pointers. So the start, mid, and end pointers in our binary search. So the space complexity is going to be constant. It's going to be big O of 1, right? And that essentially wraps up the overview of the solution. And now it's time to go over the coding portion. Now let's write out the solution. So the first thing that we're going to do is to find the lengths of nums1 and nums2 array respectively. So we have int m equals to nums1.length, int n equals to nums2.length, and then of course the length of the merged array is going to be m plus n, right? Now in the edge case that I talked about before, right, if m is greater than n, so nums1 is longer than nums2, then we just need to swap those two arrays. So return find median sorted arrays of nums2 and nums1, right? Perfect. And now let's go over the binary search. So our start pointer is going to be at index 0, right? Our end pointer is going to be at index m, right? And then while start is less than or equal to n, which means we still have a range of elements to search for, then we're just going to compute indexes I and j. So int I equals to start plus n divided by 2, the midpoint, right? Int j equals to merged length plus 1 divided by 2 minus I, right? Now, as I talked about before, there's essentially two possibilities for the maximum value of the left half, right? So let's go over those. So int max left, we'll call the first possibility a, right? Equals to integer dot min value, right? Because we have to handle the edge case in which I is equal to 0, as we talked about. So if I not equal to 0, then max left a equals to nums1 at index I minus 1. And yeah, so if max left a is integer dot min value in the code that we're going to write down below, then we know essentially that it's not a possibility, right? So int the second possibility for the maximum value of the left half, right? So max left b equals to integer dot min value, right? And then we have to handle the edge case in which j equals to 0. So if j is not equal to 0, right, then max left b is going to be nums2 at index j minus 1, right? And now let's go over the possibilities for the minimum element of the right half, right? So int min right a equals to integer dot max value, right? And again, handling that edge case, if I equals to m, right? So if I not equal to m, right, then min right a equals to nums1 at index I, right? And then for the second possibility, for the minimum element of the right half, if min of right b equals to integer dot max value, right? So if j not equal to n, right, we have to handle the edge case in which j equals to n, then min right b is going to be nums2 at index j, right? Okay. So now let's go over essentially our case breakdown, right, for how we modify our search range, and how we modify our search range if we didn't find the correct index I, right? And if we found the correct index I, let's first go over that, right? So if max left, so we know that we found the correct index I, or the correct partition, if, remember, the two constraints that I mentioned are satisfied. So if max left a less than or equal to min right b, and max left b is less than or equal to min right a, right? Then if the length of the merged array is odd, right? So not equal to 0, or we could say, is it more clear if we say equals to 1, or yeah, I mean, yeah, we'll just say if it's equal to 1, that means it's odd, right? Return, we need to return, yeah, we need to return double, right? So we'll cast the double, and then the maximum of max left a, max left b, right? And then if not, which means that the length of the merged array is even, right, then we need to compute the maximum of the left half, which is going to be the maximum of max left a, right, the maximum of the two possibilities. Then we need to compute the minimum of the right half, which is going to be math.min min right a, min right b, right? And then we're simply going to return double of max left half plus min right half divided by 2.0, okay? All right, now let's go over the case of how we need to modify our search range if the max left a is greater than min right b, right? In that case, we need to update the end pointer to be at index I minus 1, right? Right, so we're moving our search range to the left, okay? Now, that's not the case, so if that's not the case, so then we're going to say we're going to need to update the start pointer equals to I plus 1, right? And then finally, yeah, if we didn't find the correct partition, we're just going to return -1, right? All right, so let's run this code and see if it works. Yep, accepted the initial cases. Let's see if it works for all the cases, and perfect. Yeah, looks like we have a pretty optimal solution. So yeah, I hope you all enjoyed the video. Feel free to check out the Leetcode link that's going to be in the description below, as well as the solution that's going to be in the GitHub below. And then I have a Quora answer that I wrote. Essentially, we're just recapping everything that I said in this video below. And yeah, don't forget to like, comment, subscribe.